All right, hello. I need to make an announcement about exam 3 before we get started. Exam 3 will cover, instead of 3.1, 3.2, and 3.3, I'm just cutting out 3.3. I have my reasons for this. The main one being that I just don't think that we have time to cover, because 3.2 is a long section. We're going to be in 3.2 pretty much until Wednesday. We'll have time to review on Wednesday too. But 3.3, so I just don't think we'll have time. And also 3.3 is about dividing polynomials. And that's really building up to this idea of the fundamental theorem of algebra. And we don't cover that in this course, so I really don't see the point. It would be nice, but it's hard to motivate that section 3.3 dividing polynomials without having like an end in sight, which would be that fundamental theorem. So instead, I'm just going to focus on these two sections. In particular, 3.2 is what we're starting today because we've spent quite a bit of time on 3.1, and just make the exam focus on these two sections. Okay, so last time we talked about the leading term information and what we can do with just the leading term of a polynomial function. So recall that the leading term of a function, the leading term is if a function p of x is a sub n x to the n plus a sub n minus 1 x to the n minus 1 dot 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 all the way down to the quadratic, linear, and constant term, that a sub n x times x raised to the n is the leading term. And just by looking at the polynomial and seeing its leading term, we can have all of this information here, which we talked about last time, so I'm not going to spend too much time letting you write this down because you already have it from last time. But just recall that if the degree is even, that means that both legs are pointing in the same direction. Both, quote, legs of the graph are pointing in the same direction, either both pointing up if the leading coefficient is positive, or both pointing down if the leading coefficient is negative. And if the degree, so remember the degree is referring to the exponent, right? The exponent on the leading term. If the degree is odd, then the legs point in opposite directions. So they're doing like down and up or up and down, depending on, again, the sign of that leading coefficient. And then I told you that we would use this fancy notation here with these infinity symbols. So I would like to look at some examples of different polynomials and apply this notation to them. Okay. So first, let me talk about that notation a bit, that infinity notation. When I say as x tends to infinity, this means we are looking at the far, quote, far right side of the graph. Okay. And when I say as x tends to negative infinity, this means we are looking at the quote, far left side of the graph. Okay. So that's what that means when it says as x tends to is how we read that. As x, that's how we read that. I mean, as x tends to infinity and as x tends to negative infinity. So this is, quote, as x tends to infinity. Oops. It's supposed to be quotes there. As x tends to infinity. And this one is as x tends to, well, negative infinity. Negative infinity. That's how we read that. Okay. So just so we know that's what that x tending to infinity and x tending to negative infinity means. So when I give you a graph, for instance, a graph of some function like a maybe some cubic graph like this, some crazy looking cubic graph, then what I would say for this graph, and if I name the function f of x or p of x is what we were calling, yeah, p of x is the function, then I would say for this particular one, as x tends to infinity, comma, p of x, and then I have to decide if p of x tends to infinity or negative infinity. Now, as the infinity symbol relates to the x values, we're talking about x values far to the right, right? P of x, though, is the output value. So when I say infinity versus negative infinity here for P of x, I'm talking about up versus down. For the x's, it's left versus right. And for the P of x, which is the output, that's up versus down. So does P of x, as x tends to the right, far to the right, is P of x tending up or down? Well, clearly it's tending up, right? It's pointing up. And as x tends to negative infinity, in this case, so look far to the left side of the graph, P of x is tending towards negative infinity. As another example, let's take some crazy looking high degree polynomial. I'll call it r of x. We tend to use these like capital letters like P and R and Q when we're talking about polynomial functions. It's just a notation. It's you could just call them all f of x if you wanted to. That would be fine. So if you have two different functions on the same page in your notes, you may, want to differentiate. Probably just best to call them what I call them. Okay, so here as x tends to infinity, so I'm looking on the far right side of the graph, r of x is tending up, so to positive infinity. As x tends to negative infinity, r of x, so look to the far left, r of x is tending up again. See the difference between these two? See the difference? P of x back here, the left side was pointing down. R of x over here, the left side, both sides are pointing up, right? Both sides are pointing up. So this tells us via those rules that I had given you last time that this must be, P of x must be an odd function. Or let's say it this way. P of x must have an odd degree. Like it must be like x cubed or something like that. You know, maybe like maybe it's p of x equals 2x cubed plus 3x squared, blah, 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 blah. The point is that the leading term has odd degree. And this one, r of x, must have an even degree. We can see that based off the fact that both of the legs are pointing in the same direction. Moreover, we can say that it must have, they both must have positive leading terms, or positive leading coefficients, I should say. I'll say lead coefficient must be positive, because those rules I put back here say that if degree is odd and the leading coefficient is positive, then left leg points down and right leg points up. That's exactly what's going on here for p of x. And then right here, for r of x, also its leading coefficient must be positive because both of its legs are pointing up. Okay. So what we're investigating here is called the end behavior of a graph, the end behavior of a polynomial function. So we are investigating the end behavior. So if you wanted to like be able to give a name to all this crazy infinity business, it's called the end behavior. So as an example, state the end behavior of each function. All right, part A, let's say p of x equals, so it's different p of x, let's say negative x cubed. Let's let b be q of x equal x minus 2 to the fourth. And let's let c be r of x equals 2x to the fifth plus 7x squared minus 5. Okay, so when I say state the end behavior, that means those infinity things. I want like statements. There will be two statements for each one of these. One that says as x tends to infinity, p of x does this, and as x tends to negative infinity, p of x does this. You'll have two of those statements for each one of these. Okay. If you have those facts written down from last time, then you can just follow straight along from these notes. They'll tell you. So that page is like critical. You can tell I keep going back to it, right? It's pretty critical. All right, so part A, p of x is a cubic thing, so it's odd degree. So things I want to note here. I want to note that its degree is odd. So it either does this kind of shape, right? One side pointing down, the other side pointing up like this, left pointing down, right pointing up, or this, the opposite version, like that. So not that, but like this, left side pointing up, right side pointing down. Since the leading coefficient is negative, which one would it be? Anybody have any idea? Would it be the 1 or 2? 1 or 2?
What would be 2?
That's right. Yes, it would be, since the leading coefficient is negative, it will be, good, this shape. Good, okay. Now what remains is we have to be able to think about, we have to analyze this picture, right? This like little sketch, I would call it, and determine what the end behavior officially looks like, right? Like the with the little infinity notation. So you start off with as x tends to infinity. You know what, I want to get it on a fresh piece of paper, get a little bit more room here. So for p of x, as x tends to infinity, p of x, and then we have to decide what that's doing, and then as x tends to negative infinity, p of x tends to blank, right? So if we know that it's of this shape, because we know that if it's odd, then it's either this or that, and if it's negative, then it must be the second one. So looking on the right side of the graph, the right side, the function is pointing down. So recall that as x tends to infinity, that tells us we're looking at the right side. And on the right side, p of x is pointing down. On the left side, as x tends to negative infinity, this is the far left side, the function is pointing up. So that's how you solve problems like this. You note the degree, you note whether the leading coefficient is positive or negative. That narrows it down to your picture, like that, or that tells you what your general sketch of a graph would look like. Then from there, you've got to be able to get from the picture to this notation, right? This notation. And how do you get there? What's the connecting piece there? It's to understand that this tells you look at the right side of the graph, and this tells you look at the left side of the graph. Okay, let's do part B now. So part B, which I'll go ahead and rewrite the function. The function was q of x equals x minus 2 to the fourth. Now, this might seem like a problem because it's not written in that polynomial function form that we like to have. It's not written in this form with all of its terms stringed out like this so that we can easily identify that leading term to find the degree and the leading coefficient and all that. It's not written in that form. This actually is a really nice form. It's factored for us. That's nice, but it doesn't tell us the information that we need about this leading term business. So any ideas what we could do? Kimberly, what do you think we could do to find the leading term of this?
Would you like unfactor it?
Yeah, multiply it out.
Mm-hmm.
You could. So that would look like, now I'm going to tell you I'm going to just go ahead and give away the trick is that you don't have to, but you could multiply this all out, which would take about 10 minutes to do, not really that long, but it would take a while, right? You can only imagine how long this would take, right? But we know that from last time we looked at some things like this, and we know that we don't actually have to multiply the whole thing out to get that leading term. All we have to do is look at the product of all of the x terms. So we look at the product of all of the x terms. That would be x times x. In this case, there's 4 of them, and you may have already guessed that it should be x to the fourth. With no, the coefficient, by the way, the coefficient on all of these is just a 1. And technically it's 1 times 1 times 1 times 1 gives you another coefficient of 1. So in other words, you can ignore the coefficient, right, and just think about what's going on with the x's. And in this case, the x is x times x times x times x gives you x to the fourth. So our leading term is x to the fourth. And that's really all we need to be able to do this problem. We don't need to know what all the middle terms are. We don't even need to know what the last term, the constant term is. All we need to be able to do this problem, end behavior stuff, is we just need the leading term. And we have it. So now we say the leading term is 4. No, I mean, sorry, x to the 4th. The degree is even, right? Because the 4, right? The 4 is even. So the shape is this or this. Okay, so that's one or the other. And since the leading coefficient is positive, right? It's just technically a positive 1, right? Technically a positive 1. I'll say parenthetically here, positive 1. Since we don't officially see it, I want to write out what it actually is. It must be the one that points up, right? It must be this shape. Okay. So you see how degree being even or odd narrows it down to 2 categories, right? But then from there, you have to be, it's either this or this, but then you have to be able to go further with that leading coefficient, the sign of the leading coefficient, to be able to tell which one it is. So it's this one, so I can say as x tends to infinity, q of x, using the appropriate name for the function they gave us, q of x, well, both sides are going to be tending up, right? On the right, so this tells me look on the right of the graph. Well, it's pointing up. Now go look at the left hand of the graph. Well, it's still pointing up. There we go. All right. Well, I'll leave that there for another second in case you're writing, and then we'll look at number C, or letter C rather. Then I think I'm going to add part D to this example. I pulled this example from the text. I think I'm going to add a part D to it. But first, let's do part C. So part C was R of X 2x to the 5th plus 7x squared minus 5. Well, there's no funny business going on here with us having to like unpack it to find the leading coefficient, leading term, and all that. We see straight away that degree is even. What? No, degree is odd. Sorry. What did I say? Even. What was I thinking? I don't know. Degree is odd. The 5, right? The 5. It's 5. That 5 right there. That's the degree. And let me just go ahead and say the leading coefficient is positive. It's a positive 2. So I'll say parenthetically here, positive 2. It's a positive 2. So we're going to have this shape. Generally, this shape. Let me draw that. I don't like that's ugly. Let me draw this a bit better. There we go. That's a bit better. There we go. That shape. So this tells me that as x tends to infinity, comma, r of x is tending to, well, on the right side of the graph, remember x tends to infinity, that's the right side. X tends to infinity is the right side. R of x is pointing up. And then on the left side, on the left side, r of x is pointing down. Okay, now I'd like to add an example I'm going to add an example and then I'll stop and see if you guys have any questions. And then I'm also going to actually graph these in a graphing calculator. And so we can see that our assumptions are true, but also see what data we're missing. and we'll go from there. So first, a new example. I want to do another one of those weird ones that we have to unpack because I don't think we got enough practice there. Let's see, PQR, I guess I'll use S of X for this new one. Let me say 3x plus, I don't know, 7 squared times 2x minus 5. Yeah, let's do that. Bit more complicated. Oh, you know what? Let me add one more thing to it. Let me add an x squared up front. So I'm going to rewrite it. You might have room to squeeze it in, but so let's say x squared times 3x plus 7 all squared times 2x minus 5. So I added an extra factor of x squared at the front. You could add it at the back as well, but if you see these problems in your homework, that a term like this will be up front. So it's still S of X. So this, again, is one of these things that looks awful. Like, how do you know what the leading term is? You feel like you may have to unpack all of it to be able to tell what the leading term is. But keep in mind, all you have to do, like this one, is look at the product of all of the X terms. So how do we do that? We look at, you do sort of unpack it. And what I mean by that is anything like this that's some binomial anything like this that's got an exponent up on it, you'll want to unpack that like this. So I know 3x plus 7 squared is the same as 3x plus 7 times 3x plus 7. And then I'll add that 2x minus 5 on the back. And now I'm going to take the product of all of the x terms. So I've got an x squared with its coefficient to x squared times 3x times 3x times 2x. That's what I'm going to look at. This will tell me my leading term. So I'm going to have x squared times 3x times 3x times 2x. So recall that the way to multiply this is you can just take the product of the coefficients, which this coefficient is technically a 1. So 1 times 3 times 3 times 2 will be 18. Now think about the x's. Product of all the x's, there are x squared times x times x times x. It's going to be x to the 5th. Adding up the exponents, remember that rule. So this is technically x squared times x to the 1st times x to the 1st times x to the 1st, and you can just say that that's equal to x raised to the 2 plus 1 plus 1 plus 1. Technically, that's what's happening, right? When you multiply things with like bases, you just add up the exponents. And this, of course, is x to the 5th. Okay, so this tells us the leading coefficient for this S of X function. It's odd. Degree is odd, and leading coefficient, so degree is odd, that's the 5, and the leading coefficient, is positive, the positive 18. We don't care if the leading coefficient is even or odd. That has nothing to do with anything. It's just about whether the degree is even or odd and the sign of the leading coefficient. So this tells me that we've seen a couple of these now, that it's this general shape. So when I go to write down my end behavior, as x tends to infinity, S of x is tending to, so on the right side, x tends to infinity on the right side, S of x is pointing up. As x tends to negative infinity, S of x is pointing, so on the left side, S of x is pointing down. Okay. So, how do you guys feel about that? Are we good? Do you need to see any more examples? We've done, I think did we do one of every case? I don't know if we did one of every case, but so let me know how you're feeling, or maybe you want to see an even negative one. I think that's the only one we didn't do. Okay, so if there are no questions, what I'm going to do now is graph these functions in Desmos. So we're going to see what these functions look like, and how good our assumptions are, like how much we're really seeing, with just that leading term. Because you might be saying, well, if all I need is the leading term, if that tells me what the graph looks like, why even ever discuss anything but the leading term, right? Why do you need any of the other parts in the middle of the polynomial function? Well, let's see what we have. Let's start with part A was p of x equals negative x cubed. Let's look at that. Whoops, not 33. So we said that on the left, the graph should be pointing up, and on the right, it should be pointing down. Let me see where I solved that. And I feel like there's not much else to say about this one. This one's pretty good. And we got the general shape of it pretty much down. All right, let's look at, that was part A. Let's look at part, what do we want to look at? Let's see, part B was x minus 2 all to the 4th power. Yeah, that's pretty much the shape that we sketched out for that one as well. Pretty much like a parabola, right? It's pretty much like a parabola. Also note, this minus 2 tells you that you should take the base graph of x to the 4th and shift it right by 2. If you recall from section 2.6, transformations of functions, subtracting inside the function means you shift to the right. And that's exactly what's happening here. This base graph of x to the 4th was shifted to the right by 2 to get this graph. Anyways, that's not really the point of this part of the lecture, though. So let's go on to the part C, which is 2x to the 5th plus 7x squared minus 5. Now, this one is the first one that I feel like looks pretty wacky. If we look at, if you're looking in the notes we just did, where's part C? There it is. All we really said is that it had the same general shape as like a cubic graph, right? On the right, it should point up, which it definitely does. And on the left, it should point down, which it definitely does. But this junk happening in the middle, we didn't say anything about that. We don't really know what's going on here, right? We just kind of expected maybe a general shape like this, just like pointing down and then pointing up. We didn't expect this wild like roller coaster thing in the middle. That's something that we are missing from just looking at the leading term. The leading term only tells us about end behavior, extreme behavior at the infinities or near the infinities, all the way over here on the right and all the way over here on the left. It does not tell us about what's happening locally, like around 0. Or just at smaller numbers. It doesn't tell us what's happening. Let's look at the last one that I gave, which was the x squared times 3x plus 7, and then 2x minus 5. Now, this one, whoa, really crazy. Oh my goodness, that's like worse than I really wanted. What have I done? Where is the bottom of it? hang on, did I type it in wrong? No, that's okay. We're not. This was so bad. Okay, well, this is an example of a polynomial function that has odd degree, right? Its leading term is 18x to the fifth. So we expected on the extreme right that it should eventually go off to infinity, which we're seeing on the right. It does. It's going up to infinity. And then, sorry, let me scroll down here and see if I can make sense of how far down do I need to go. There it is. There's the one piece that's by itself pointing off to negative infinity. Now, all of this junk happening in between, I'm sorry, I'm using my laptop mouse, which is a pain. Here we go. All of this craziness happening. Oh, look at that mess. What a nightmare. All of that is not, we don't know anything about that just by looking at the leading term, right? In fact, it even gets worse. It keeps going. There's another little bump that goes, I guess, that spikes down really far down here somewhere. My goodness, what a terrible, I've never made up such a terrible polynomial just off the cuff like that. So we don't know anything about these x-intercepts either. Okay, so we see that, what are we saying here? What was the point of all that? That the leading coefficient is, the information is quite powerful in that it tells us the end behavior like pretty quick, right? As long as you know how to interpret it, then it's like, it's a lot of information just coming from one single term of the polynomial. What about all that junk happening in between, right? That's what we're going to start considering now. That page that I gave you that has all that information for you to study, I want to tell you there is a nice version of that on page 293 in the text. So if you go to your ebook and go to section 3.2 and poke around in that section. Now the ebook is not like, I don't think the pages are numbered exactly the same, but you'll find this. You may not be able to read this, but it says end behavior of polynomials. There's a nice chart here that describes each case. The two odd ones with positive, negative coefficients, and the two even ones with positive and negative coefficients. That's a really nice picture that sums up pretty much everything I just talked about right there in one nice, easy to study picture. Also, I should say, instead of using the P of X notation there, instead of like P of X or R of X for their functions, let's see, can I show you? They're using just Y. You can't see it, probably. They're saying they're using the letter Y instead of like P of X or R of X or Q of X. That's just the notation they chose to use in that little box. Okay. So let me have 1 second to think about the next step. Okay, so the next step is investigating, I'm going to call it local behavior. So not end behavior, not behavior near really high x values, not behavior near infinity. We're investigating now local behavior. What does this mean? We will be looking at the x-intercepts of the graphs of polynomial functions. So how do we find the x-intercepts of polynomial functions? This amounts to setting the function equal to 0 and solving for x. I mean, that sounds simple enough, but that is quite a loaded statement, right? That could be, I mean, I could plot down a polynomial function like in 1 second that would be pretty much impossible to solve for x without a computer, right? So in this section, I'm going to be very careful, obviously, about the functions I give you and ask you to solve by hand because they need to be doable. But basically, all we're going to be doing is just this, setting a function equal to 0 and solving for x. That is how you find the x-intercepts. So let's consider as an example, just a quick example, consider p of x equals x squared plus x minus 6. Let's find the x-intercepts. Well, it's just quadratic, so we should be able to do this. In fact, this was part of 3.1, was finding the x-intercepts of quadratic functions. How do I know it's quadratic? Well, it's degree 2. So it's a very special polynomial function that is degree 2. And we have practice finding the x-intercepts of polynomial functions like this. So what do? We set the function, as it says, set the function equal to 0 and solve for x. So x squared plus x minus 6 equals 0. Solve for x. How do you solve this for x? Well, so we have tools. First tool is factoring. Anybody remember what the other major tool is specifically for this kind of function, for solving it's gone from a function to now an equation because I've set it equal to 0. What is that major way that we had to solve a quadratic equation? It's a formula called the quadratic formula. Negative b plus or minus square root of b squared minus 4ac all over 2a. Let's factor this one. This one is pretty easily factorable. Let's just factor it. So it's easier than plugging into this. We need to factor this by like a traditional method, thinking about two numbers that give a product of -6 that add to give a +1 here. So I'm thinking of a 3 and a 2, and one of them needs to be positive and one needs to be negative so that I get a product of -6, but I also need to add them to get a +1, so I better make the 3 positive and the 2 negative. Okay, then I say, well, if I have the product of two things, so this whole factor times this whole factor equal to 0, then I can set them each equal to 0 separately, which is the whole point of factoring. That's the whole point of factoring, is that you can then get them to these little linear equations, and then you can solve them like this pretty easily at that point, just solving for x. When I say easily, I mean like relative to like using the quadratic formula. So then my x-intercepts are, so I still have to remember that I'm not completely done at this point. I mean, I'm mostly done, but really the last step is to actually write the x-intercept for each of these x values, and you just plop them into their own little coordinate points with a y value of 0 for each one, because that's what when you force the function equal to 0, you're saying let the output be 0. Let that output be 0. That'll tell me where I'm crossing the x-axis. Let the y value be 0. This will tell me where I'm crossing the x-axis. So this is an example of what we'll be doing with higher degree polynomial functions, finding the x-intercepts. So what if we have a higher degree polynomial? Okay, I'm going to go ahead and enumerate this as example 2. Find all of the x-intercepts of each function. All right. Say p of x equals, let me look at those. Where are those problems I gave before? No, that's a bad one. No, that's a bad one. Okay, they're all bad. Okay, let me make one up then. Let's say x cubed. Shoot. X cubed plus x squared minus 6x. There's 1. And then -7. -7, let's say x to the 4th minus 7x squared. Oops, I meant to make that cubed. 7x cubed plus 12x squared. And, oh God, I didn't even name it. This is r of x. R of x equals x to the 4th minus 7x cubed. I'm trying to be very careful about the examples I'm coming up with here so that they don't give us anything we don't want to look at yet. And now a last one. Let's see. Let's just do x squared minus 16. Just another quadratic one. Okay. Part A, p of x is x cubed plus x squared minus 6x. Now, when the degree is higher than 2, you only have one tool, and that's factoring. Well, pretty much at this point, yeah. When the degree is higher than 2, our only tool is factoring. Because if the degree is higher than 2, you can't use the quadratic formula because it's not quadratic, right? It's cubic. So when the degree is higher than 2, when it's not quadratic, the only tool you can use is factoring. But note that when I take this thing and I set it equal to 0, which is the standard procedure, can't I factor an x off of all 3 of these terms? Like that. Okay, any questions about that? You see what I did? Pulled an x off of all 3 of those terms. Okay. And then I say, oh wait, this is a nice quadratic polynomial now. It can fairly easy to factor. In fact, it's the one we just dealt with, so I know it can factor into x plus 3 times x minus 2. And now what I do is I set each of these equal to 0, each of these factors equal to 0 individually, including that first one, the x by itself, and I solve each one. So of course, the top one is already done. So I'm getting x equals -3 and the same two from last time. So my 3 x-intercepts are -3, 0, 2, 0, and also 0, 0 from this one. Okay, so that's how some of these problems can go. You'll have extra x values attached to a nice quadratic function that you're used to dealing with, or at least more comfortable dealing with than cubics and whatnot. Let's look at that happening with part B again, or similarly with part B. So r of x equals x to the 4th minus 7x cubed plus 12x squared. Set this thing equal to 0 first, and we're going to solve for x. Does anyone see what I can factor off of this polynomial? I can factor an x squared off of all 3 of these terms. So it's very similar to part A. Very similar to part A. And then I can say, oh, look, it's a nice quadratic. I know I can factor this. 2 numbers that multiply to give 12, that add to give -7. Well, let's see, what would that be? So here's my setup. 2 numbers that multiply to give multiply to give 12 and add to give -7. It's got to be a 3 and a 4, with both of them being negative. And then I set each of these factors equal to 0 individually. Whoops. And x squared equals 0 just means x equals 0. X minus 3 equals 0 means x is 3. And x minus 4 equals 0 means that x is 4. So I have 3 x-intercepts again. 1 at 0, 0, coming from this term, or this root rather. 1 at 3, 0, coming from this root. These are so-called roots of the equation. And then 1 at 4, 0, coming from this root. So what's the difference here? The difference lies right here, where we have from the last one, the last problem, we had just x equals 0, giving us a x-intercept of 0, 0. And here we have x squared equals 0, but does it really matter because it just ended up giving us still 0, of course, right? So does it matter? So next time I want to investigate this issue, because there is something to say here. And it's called multiplicity. But we'll save that for next time. Let's get this last example done. Part C, and then we'll be done for today. Okay, set it equal to 0. Solving x-intercepts, you set the function equal to 0 and solve for x. You may notice that this is a nice quadratic that can be factored. In fact, it's a difference of squares. If you recall the difference of squares formula, a squared minus b squared is the same as a plus b times a minus b. Or you can just say, well, I'm just going to solve it directly, because you can do that here. Add 16 to both sides. You can only solve it directly when it's of this form, like x and then a constant. If there's any other x terms, you can't do this method. And then take a square root on both sides, so plus or minus. Don't forget to introduce plus or minus when you're solving it this way. And then square root of 16 is 4, so I get plus or minus 4. So my two roots are -4 or 4. And that's giving me these two x-intercepts, -4, 0, and 4, 0. If you solved it by factoring it, it would come out exactly the same. Because you would have x plus 4 times x minus 4 equals 0, split them, and etc. Okay, so next time I want to look at graphing these things using their x-intercepts to help graph them together with the end behavior, and also investigating that issue of multiplicity. You guys are good to go. You can stick around if you have any questions. I'll see you Monday.